Tanks stormed onto World War I battlefields as steel giants, seemingly unstoppable and immune to enemy fire. Their image as rolling fortresses persisted into World War II, with panzers appearing invincible as they swept across Europe. But for the crews inside, the tank was less a fortress and more a target, every moment shadowed by the threat of sudden destruction. The real battle wasn't just on the front lines, but in the labs, where engineers and metallurgists raced to outsmart each other. As armour thickened, shell designers responded with smarter, not just stronger projectiles. The science of defeating tanks became a contest of physics and innovation, not brute force. Tank crews knew their survival depended on millimetres of steel and microseconds of impact. Every hatch, seam and viewport was a potential weakness. The myth of invincibility was shattered by the harsh reality of calculated risks and relentless technological evolution. At high speeds, steel acts more like a liquid than a solid. Early armour-piercing shells relied on kinetic energy, but as armour improved, these projectiles often shattered. The breakthrough came with hydrodynamic penetration, shells designed to focus immense pressure at a single point, momentarily softening armour for penetration. Metallurgists crafted alloys that balanced hardness and ductility, creating AP shells that could pierce armour thicker than themselves. Even a failed penetration could cause deadly spalling, sending lethal fragments into the tank's interior. In tank warfare, even a safe hit could be fatal. Engineers wanted more than just holes in tanks. They aimed to destroy everything inside. The solution base fused shells with a delayed action explosive. The hardened nose punched through armour, while the fuse at the base triggered a split second later, detonating inside the tank. This transformed the shell into a precision weapon, maximising internal damage. Crafting these fuses required miniature engineering marvels, robust enough to survive firing, yet sensitive enough to detonate at the perfect moment. The result was catastrophic for crews, turning tanks into infernos. The shift from brute force to engineered intelligence redefined anti-tank warfare. The shell became a complex delivery system, not just a projectile. Tank designers countered powerful shells by sloping armour, doubling its effective thickness and increasing ricochet chances. Sloped armour, as seen on the T-34 and Panther, made standard-pointed shells deflect harmlessly. The answer? The armour-piercing cap, a soft metal tip that deformed on impact, gripping the plate and preventing deflection. This allowed the main penetrator to strike at a better angle, improving penetration. To maintain speed and accuracy, a streamlined ballistic cap was added over the blunt, armour-piercing cap. The result, the APC-BC shell, a multi-stage projectile that combined penetration and aerodynamics. This innovation kept pace with evolving tank defences. The battle between shell and armour became a contest of shapes and materials. As tanks grew heavier, engineers sought more velocity, not just bigger guns. Enter the subcaliber projectile, a dense tungsten dart fired from a larger gun using a lightweight sabot. The sabot fell away after firing, leaving the dart to strike at incredible speeds. APDS rounds could exceed 1,200 metres per second, punching through even the thickest armour. The British 17-pounder with APDS rounds could defeat German Tigers and Panthers at long range. This leap in technology proved that speed and density could outmatch size and explosive force. Sub-caliber projectiles set the stage for modern anti-tank ammunition. The science of velocity and focus became the new standard. No tank was ever truly safe. Survival depended on tactics and skill. Crews used terrain, hiding their hulls and exposing only the turret to minimize their target profile. Knowing enemy weak spots and prioritizing threats became essential. Distance was a key ally. Engaging at maximum range reduced the enemy's penetration power. Tank duels became battles of positioning, timing, and quick calculation. Veteran crews could outfight better-equipped foes through experience and cunning. Even a slight angle could mean the difference between a ricochet and a fatal hit. In the end, human intelligence and adaptability were the ultimate defences. World War II forged the relentless cycle of tank and anti-tank innovation. Scientific ingenuity, not just brute force, drove the biggest breakthroughs: liquid-like steel, delayed action fuses, and sub-caliber darts. Modern tank rounds, like APFSDS, are direct descendants of wartime inventions. Composite armours and new shell designs continue the contest. For every new defence, a new offence emerges. The tank's survival still depends on innovation, balance, and crew skill. In warfare, adaptation, not size, determines who prevails.